Hi all, it's Mr. Yeager for Physical Science. I'm now looking at nuclear reactions. We're going to look at nuclear reactions today, how to balance some nuclear reactions. Actually, I need to probably grab myself a periodic table, so let me do that real quick so I can try to help balance some of these. All right, and we are looking at basically what are nuclear reactions. We're going to look at, sorry, let me change the size of this. I'm getting all distracted with different things here. There we go. All right. We're going to look at the types of nuclear reactions that are out there, and then we're going to look at pros and cons of nuclear power as well, where these reactions take place. So what is a nuclear reaction? Okay, it is a reaction that occurs inside the nucleus. And later on in physical science, we start looking at chemical reactions. Chemical reactions occur outside the nucleus. We don't do anything anymore with the protons and neutrons. It's going to be all electrons. This is very specific, where it's just the protons and neutrons being involved. Because those are involved, it's very, very, very likely we're going to change into a new element, because when the number of protons changes, we have a new element. All right? So you can see with the picture here, basically, where a neutron comes on in, hits the nucleus of the atom, and it might split up into different pieces. Those protons and neutrons, they still try to hold together, but they might be broken up into multiple nuclei. All right? So each of these, sorry, I'm going to kind of increase the size so you see it a little bit better and not turn it sideways so you don't get sick. All right. There are two types of nuclear reactions out there. One is fission. Okay. Fission is where the nucleus splits. All right. I don't feel like I have to underline it again, but there it is. Fission is where the nucleus splits, which means the elements become smaller. Okay. You will produce smaller elements because you're smashing that larger nucleus into multiple pieces. Fission does produce large amounts of energy, but it also produces large amounts of nuclear waste. Okay? There are elements that basically continue to be radioactive, but don't really do anything. They're not useful to us because they're essentially too dangerous. All right? This is the process that occurs at nuclear power plants. So again, kind of already going at the pros and cons of nuclear energy. We can get a lot of energy out of it, but the downside is we do have that waste, that radioactive waste afterwards that could be very dangerous. So fission splits. Okay? Fusion, I feel like this one's large enough for you to see. Fusion is where we have the two nuclei combine. We have multiple objects trying to combine, multiple nuclei trying to combine. All right? No, it doesn't want to increase for me. Oh. Fun. All right. Fusion is where we're going to combine. The word fuse means to put together, okay, to glue together almost. All right. This is where we will produce a larger product than what we started with. All right, because we're essentially combining two elements to form a larger one. We're adding more protons together. This will also produce large amount of energy, and it actually does not produce much waste. Okay, we basically say it doesn't produce waste. All right. The unfortunate thing, though, is this really is only occurring well in stars in the sun. Well, I mean, I shouldn't say unfortunately. We wouldn't have our solar system without it. But what I'm saying is very, very, very difficult to get it started on Earth. Okay, fusion needs very, very high temperatures and pressure to get started. If you can't do that, it's not going to happen. All right, so we still have not found a really good, safe, feasible way and cost-effective way to have fusion right now, just because it's so difficult to do it. You have to maintain an extreme star-sun-like temperature in order for it to continue to occur. But fusion is where we do develop larger elements. Okay. So what we're going to do is we basically do something called nuclear reactions, okay? Where you essentially have to figure out what are you producing? What are the new products that are coming out of it? Or what is the radiation involved with it? The key to nuclear reactions is basically my two statements underneath here, okay? The mass number of the reactants has to equal the total mass number of the products. All right, the atomic number of the reactants has to equal the atomic number of the products. Now, the thing is, we haven't really done reactions yet. Reactants are on the left side of an equation. We call this a nuclear equation. Products are on the right side. Right side of what? The arrow. Okay? Left side of the arrow is what you're starting with. Right side is what it's turning into. Okay? We have to look at the mass number, the top number on an element symbol, basically how we kind of write these elements out as we've gone over. And this number, this 238, has to add up to the two numbers on the other side. So we have to have the total number, the sum of the numbers, add up on both sides. Same thing with the atomic number. All right? So let's basically try to jump right into some of these. Okay? So if I said, let's practice some, let's see how we can deal with this. Okay? So I have my example right here. You can see I have 24294 Pu, which is plutonium. It's releasing, this is not helium, this is actually an alpha particle, which sometimes you're going to have to identify. That's the types of radiation that we just did. Well, the thing is, I want to figure out that other element, what that other product. So how do I do this? Well, what's the total mass number on this side? That's 242. 242. On this side, I have 4. So this side, I have to add up to 242. So 4 plus what, okay, is 242? I just subtract those two. It's 238. All right? 238 plus 4 is 232. 242, not 232. 242. All right? What about the atomic number? Because 238, I don't know what, I can't identify an element by the mass number. What about the atomic number? Well, we got 94 on the left side. 2 plus what is 94? The answer is 92. Then if I look on a periodic table for number 92, that's uranium. So your answer is 23892 uranium. You need to get all of those things together. All of it has to be together to be correct. All right? If I look at the next one, I'm looking for the reactant. I'm given the products, sulfur, and this is a beta particle. Right? So if I look at this one, this is kind of interesting. I just add up the two mass numbers. 32 plus 0 is 32. So this still has the same mass number. But what do I do down here? 16 plus negative 1. 16 plus negative 1 means I have to subtract 1 is 15. What's 15 on the periodic table? 15 is, there it is, phosphorus. So this was phosphorus. It released a beta particle and became a sulfur atom. What about the next one? All right, this one's a little bit trickier because we got something else that happens sometimes. Okay, we have one element, 25298 California. Okay, but I need to figure out what the other part is. Over here, I have this number right here is a coefficient. It's telling me how many of these things I have, how many neutrons I have. So this is telling me I have 3 neutrons. So it's like writing 10n plus 10n plus 10n. Instead of writing all of those like that, I just write 3, 1, 0, n. I have 3 of these neutrons. So for this, I have to basically multiply that number into both of the numbers next to the neutron. So if I look first at the mass number, on this side, since I have everything on the product side, let me add that up. So 3 plus 259 is 262. On this side, it's 252. So 252 plus what is 262? 10. Now I look at the math or the atomic number. 3 times 0 is 0. So the neutrons aren't telling me anything about the mass number. So I just have to match 103. 98 plus what is 103? That's 5. And 5 on the periodic table is a boron. Next one. I have 5526 iron, 5525 manganese. Well, it looks like the mass numbers are the same. So this provides 0 for the mass number. This 25 is 1 less than 26, so I'm actually losing 1. Hey, what's 0, negative 1? That's a beta particle. And then the last one right here, 15.8 oxygen. I got this weird thing, don't worry about it, let's just use it. It's called a positron. You're not going to see that ever again. It provides 0 mass number. Over here it's 15, so I have to have 15. 15 plus 0 is 15. And then what plus 1 is 8, 7, that's nitrogen. So that comes out to be nitrogen. So again, I know I did it quick. Go back and kind of watch it a couple times if you need to. But again, we're just matching up mass numbers and atomic numbers. Okay? So the last thing I need to quickly go over is what is the pros and cons of nuclear power. So what are some things that are probably going to come up about what's good and bad about nuclear power? Again, this is created by nuclear reactions in power plants. Pros, you get lots of energy. There's lots of energy you can get from nuclear power. It's going to be clean energy. What I mean by that is no greenhouse gases. It releases almost no carbon dioxide and stuff, so it's not going to lead to global warming. This would actually reduce global warming. We have created some new products that have helped us through nuclear reactions. Okay? Basically, like medicine and stuff has helped us, radioactive isotopes that we use to help diagnose us and things like that. That has helped us. There's been some protective gear and things like that have been created. We even have nuclear radioactive atoms in our smoke detectors. Americium is in smoke detectors, so it's keeping us safe. Those are the primary things that we got to do that are your pros. Lots of energy, clean energy, and created some new products. Cons, the main ones clearly, first off, radioactive waste. Okay, radioactive waste, major bad one there. 2, I just blanked on that. Oh, it can cause thermal pollution. So if you remember what thermal pollution is, okay, it can heat up lakes. It can heat up lakes and ponds. It could possibly destroy waterways. And then last, another good con, it's creating up some new products, but obviously we could have meltdowns or nuclear bombs from it. Okay, if it's obviously put into the wrong hands. So those are the primary ways. I mean, you could probably read through some more with it of what's involved. I mean, cost is expensive on both sides with it. You could put that as a pro for being cost effective in the long run, but con for the initial upfront cost. But there's a couple different things involved. But these would probably be the ones that you could pick out the fastest, okay, involves of what's pros and what's cons. All right? That's it. Thank you very much.